Welcome to this tutorial on how to set up the Planetary Processing Multiplayer SDK in LÖVE. Let's start by opening LÖVE 2D. Unlike most game engines, LÖVE 2D does not have an editor. It is more of a framework for Lua code, so we will have to create our project manually before we can run anything through it. Instead, create a main.lua file to be the basis of our LÖVE 2D project. Open a terminal in the same directory as main.lua, and use the command git clone to download the Planetary Processing SDK. The command can be found in our Quickstart documentation in the description. Finally, we're going to create a conf.lua file. Open it up and add the following code to enable the LÖVE 2D console for printing and debugging. These are the only files we will need for a basic multiplayer game. We're going to start with some basic code to integrate the SDK. In LÖVE's load function, we need to add two functions, sdk.init and sdk.join. Init establishes a connection to your game server using the game ID from the backend web panel, and join adds your player to the server itself. Technically, this is all you need to connect your game client to your game world. If we update our game parameter, we can start up the game world and connect to it. Run your game server using the Actions button and select Start Game. Each new game repo starts with some default demo code. This code creates a forest filled with NPC cats. If we run our LÖVE client, we can see our player appear on the server map. However, although the connection is established, we aren't doing anything with that data on the client side, hence the black screen. You can change the color and appearance of players in the Entity Settings section of the web panel. This means you can customize your panel map to keep track of important entities more easily. Placing the sdk.update function inside LÖVE's update function will stream information about all the entities on our server to our game client. We can then use LÖVE's draw function to visualize these entities. Iterate over the entities near to the player and draw them based on their server-side type. We are going to represent the different types of entities, cats, trees, and players, by the first letter of their name, T, C, and P. If we run our game client again, we can now see a slightly inaccurate version of the game map in the top left of our window. However, you will be able to see the C cats moving. The reason everything is drawn in the top left corner is because LÖVE 2D's draw function only uses positive world coordinates, and its origin, 0, 0, is in the top left, whereas Planetary Processing's game world uses negative and positive coordinates and a centralized origin. We can resolve this by offsetting everything we draw by half the game window's width and height, essentially moving the origin, 0, 0, to the center of the game window instead. Create a pair of variables to store our world offset. When the window first loads, calculate its center point, then apply the offset at the start of the draw function, so that it affects all the entity graphics which follow. If you run your game client again, the window will now be centered on the game world's 0, 0 coordinate, where the player spawns. You may notice that the client map still doesn't quite match the server map. This is also because of LÖVE's top left origin point, since its y-axis points towards screen bottom, whereas the Planetary Processing world's positive direction is screen top. So the entire world is flipped upside down. There are two ways of resolving this. Either match the server to the client or the client to the server. To match the server to the client, use the game settings on the web panel to invert the map. To instead match the client to the server, you can manually adjust the positioning in your code. Anything we draw based on the server coordinates must be flipped to correct the inverted y-axis. Create a class constant called inverted y-axis as a reminder of the inversion and set it to -1. Then multiply our entity's y positions by that negative constant to invert them to the correct position. The final alteration we want to make to sync our world map with our game client is to zoom in on the player. Your game world loads in square segments called chunks. To optimize processing, players on the server will only load chunks in a 3x3 grid around them. By default, each chunk is 64 units, which is a good size for our letter-based graphics. To implement a zoom, create a variable with a value of 10. Then apply that variable to each drawn entity's x and y position to scale the world to an appropriate size. When you start using actual graphics and textures, you can tune your zoom and chunk size in the web panel to best fit your game. If you run your game now, it should be starting to look a bit more like something you can play. So let's start interacting with our game server. We'll add some code to our update function to handle WASD keyboard inputs to move the player. When a key is pressed down, an X or Y value is stored in our movement table. These values are either a positive or negative speed value, standardized by applying delta time, dt, to remove the influence of FPS. Once we have checked each key, we can start sending our movement message to the server. It is always best to check that a key has actually been pressed before sending a message to the server, since sending messages every update frame can cause a lot of network traffic and slow down your game. Remember that the y-axis inversion affects messages to the server as well as from it, so we must negate our y movement value before we send anything. The default server code is already set up to receive basic player movement, so we can simply use sdk.message to send our movement to the server. If we run the game, we can now see the player moving around the nearby area. Currently, our viewport is fixed on the world, but we can change this so that it follows the player instead. Like syncing our map origins before, this can be done by offsetting where we draw our entities, but this time in relation to the player. Create a pair of variables to store our player relative offset. Each update, calculate the position of the player entity. Since our other players online will also be using the same entity type player, we identify this specific player using the ID of the game client itself, stored in the sdk.uuid. As before, we need to apply the offset at the start of the draw function, so we modify our previous translation to include the player offset. Now our camera will follow the player around. If you have a very powerful PC or monitor, you may notice some lag after using the keyboard inputs for a while. This is because the LÖVE update function is called every frame, and with a game this basic, you can be looking at anywhere from 500 to 1000 frames a second, which is pretty amazing, but also terrible, since the game server's default update rate is only 30 ticks per second. You can see your game's FPS by adding LÖVE's getFPS function to the drawing phase. By default, VSync is enabled for the LÖVE 2D window, and this limits the frame rate naturally, since VSync tries to match a game's FPS to its monitor refresh rate. You can see my game is capped around 60 FPS, matching my screen's refresh rate of 60 Hz, but some displays can go as high as 240 Hz. So for every second an input key is pressed down, at least 60 messages are being sent to the server, which only wants to process 30 at a time. Now, the server tick rate is adjustable in the settings section of the game panel. However, it is capped at 100 TPS. This is fine for my 60 Hz VSync monitor here, since I could set it to 60 ticks per second, but it might not be for a player with a faster display, or if you want the player to be able to disable VSync. To help synchronize the FPS and tick rate, you can instead apply a limit client-side to how often the message triggers. Create two variables, one to count the time passed and another for the desired time of each tick. Here we are aiming for 30 ticks per 1 second. Wrap this limit around our message sending process by adding the time elapsed in seconds to the message limiter variable. Whenever the time elapsed becomes greater than the tick rate, send the message and reset the limiter. This is just a simple implementation which allows the game to process at its maximum frame rate while the message rate is limited. As you build your game, you can optimize this for the best result. This covers all the essentials for getting a working multiplayer demo up and running. You can now start customizing your client and server-side code. For example, you might want to resize your game window. This can be done using the standard LÖVE implementation. Set the window resize property to true and change the size in LÖVE.load. Then use LÖVE's resize function to make sure your world offset stays up to date with the new window size whenever it changes. The server-side code also uses Lua. You can edit this by going to the Games section of the web panel. You can either change some code in the web editor and run it, using the Reset Simulation tick box to clear the old chunk and entity code, or, if you are familiar with Git, download the repository to your computer using a terminal to execute the git clone command, followed by the repository URL. Each of your entities has its own server-side Lua file. The init file runs whenever a chunk in your game world is loaded. and the events Lua file handles triggerable events, like players joining or leaving. For the moment, let's just make a small change to the tree entity's behavior to make them gravitate towards the center of the map. In the update function, get the tree's current position relative to the origin, 0, 0, 0. Invert it to get the position of the origin relative to the tree. Add a drag factor so that the tree will only gradually move towards the center. Then use the entity move function to apply that movement. Deploy these changes and reset the simulation to run these new gravitating trees. Our trees are now being slowly drawn into the center. We should be able to see the same effect in-game. To make more changes to your chunk and entity behavior, either use the inbuilt web editor again, or simply use Git as you normally would to edit and push your clone files to the server. Then deploy them from the Actions menu. We have a server-side tutorial video for getting started on editing your game world, or documentation for more details. Thanks for watching this tutorial on how to integrate LÖVE with the Planetary Processing Multiplayer Toolkit. If you want to stay up to date on everything we do, or need help, check out our Discord in the description below.